Hello, Mr. Claudia here. Today we are going to continue to learn about curve sketching. If you remember in the last lesson, we looked at how to find out if a function is increasing or decreasing by using the derivative. Today we're going to look at the critical points in detail. And we're going to look at how this allows us to determine where a function reaches a maximum or minimum point. So just to start off today, let's just draw a nice function like this. Just a quick sketch. Oops. And let's just talk a little bit about a nice cubic function like this. So I can see, if you remember from yesterday, my function is increasing in this section. So I would say it's increasing in this region up to this point. And then the function starts decreasing down to this point. And then the function starts increasing again. So if you look at this, you can really find out that, well, what is this point then? This point that I just kind of put a dot at? This would have to be the max point. And then when I go down here, this point here would have to be a minimum point. Those are both points. So when I'm talking about, for this function, f of x, when I'm talking about a maximum point, that's the point where the curve goes from increasing to decreasing. When a function changes to increasing, from increasing to decreasing, this is a what do we call it? We call it a relative max. Or you might also call it a local max. Similarly, when you go from decreasing to increasing, that low point, that's a minimum. That's a relative minimum. Your relative min or a local min. There are two types of language we use. In the regular grade 12 course, like a non-IB course, we use local min and local max, but IB really emphasizes relative min and relative max. So I'll try to use both of those terms in our course. So it's really, to find the max and min points, pretty straightforward. A max is where you go from increasing to decreasing. A min is where you go from decreasing to increasing. Now what about at these min and max points? What's actually happening there? Well, at this max, the function's neither increasing nor decreasing. If I looked at that point in detail and I looked at the tangent line, well, the tangent line is horizontal. Same with the min. The tangent line is horizontal. Therefore, the slope of the tangent is 0. Therefore, the derivative is 0. So, in other words, to find these max min points, I have to have a spot where the derivative is 0, or, as we learned yesterday, the derivative does not exist. So essentially, I have to find the critical points. So our rule then for finding the max min points, we're saying to find the relative max min points, or what we might call the extreme points, we would use something called the first derivative test. Actually, before I go on, why do we call these relative max and min points? Well, the point is that there could be many different, if this was like a 7th order function, it could go up, down, up, down, up, down, up, down many times. I have to know what each of those max min points are. So there could be a lot of max points. It's not the overall max of the function, it's the max of that little hump. So that's a local max or a relative max. We'll learn in our next chapter about the absolute max. That's the highest point that the function obtains over the entire interval. For this function, it might go on, and there might actually be the absolute max might be somewhere way up here. But for now, we're just talking about the local humps and bumps or valleys or peaks and troughs or whatever you want to call it. So to find these relative max min points, we're going to use something called the first derivative test. To use the first derivative test, we need to find all the critical numbers. Now, at the critical number, if the function changes from positive to negative, then you have a max point. If the function changes from negative to positive, you have a minimum point. If the function does not change, if the derivative does not change sign, then there is no max or minimum at that point. Before we do this first derivative test, you're going to find, again, the language looks confusing, the math language, but once we do it, you'll find this is just an extension of yesterday's lesson. But before we go on to an example, let's just talk a little bit about what this means. So let's say I have a function that looks like this. Beautiful quadratic function. Okay, I know that the slope of the derivative, or the slope of the function here, slope of the tangent line is 0. I know at this point then the derivative is going to be 0. So that corresponds to the critical point. Now, if I were to look at some point on to the left of that, I would be able to clearly tell you that it is increasing. So the derivative is greater than 0. The derivative is positive, positive slope. And if I looked at a point to the right of that critical point, I could tell you without any doubt that this is decreasing, which means that the derivative, the slope is decreasing, or the function is decreasing, so the derivative is negative. Well, according to our first derivative test, if the derivative changes from positive to negative at this critical point, critical number, then this has to be a relative max or a local max. So this is a relative max. Similarly, if I have a function that looks like this, well, I know that this point, this is my critical number, and I know that on this side, my slope is negative, so my derivative is negative. Here my slope is positive, so my derivative is positive. First derivative test says if I go from a negative to a positive at a critical number, then this is going to be the relative min, or the local min. Now, let's say I have a function that looks like this. We're going to look more at these this week, but I have a critical number right here. It's a point of inflection, which we'll learn about later this week, or later this chapter. To the left of that critical number, the slope is positive. The function is increasing. To the right of that critical number, the slope is positive. The function is increasing. Well, if there's no sign change on either side of the critical number, then this is not a maximum nor a minimum. And you can clearly see that it's not a max or a min. It's not an extreme point. So let's do 2 examples to kind of drive this home a little bit. Okay. Given the function f of x, blah, 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 calculate the critical points and determine if they are relative maxima or relative minima. This is another kind of language thing. Maximum refers to one maximum, but you could have many maximum, which would be a maxima. Like technically, that's like the right way of saying things. It's like the difference between one datum and many data points. Okay, regardless, as long as we understand what it's saying. So, maxima, minima. So what I need to do is find these critical numbers, right? To do my first derivative test, I need the critical number. So I'm going to find the derivative, which is -5 plus 8x, I believe. And, okay, so there are critical points when the derivative is equal to 0 and the derivative does not exist. Well, there's no such thing as this derivative not existing. It's a polynomial function. It exists for all x values. But we can find places where this derivative is equal to 0. So I'm going to set it equal to 0. So then I end up with 5 is equal to 8x. So I end up with x is equal, oops, hard to see, x is equal to 5 over 8. Now, what I showed you yesterday so now we need to know where is the function increasing and decreasing on opposite sides of this critical point. Yesterday I showed you how to do this sign diagram. So I'm going to draw here. This is the sign of the derivative. And we know we have a critical number at x equals 5/8. Now, I showed you yesterday how to use a table. I am just going to show you that for this situation, it might be quicker to just sub in points. Like you can almost do it by inspection. For a number less than 5/8, like 0, that would give you a negative. And for a number greater than 5/8, 1, for example, that would give you a positive. So we can complete the sign diagram for this linear expression by inspection. So it's pretty quick to do it. Okay, so now remember the first derivative test. So you go to your critical numbers. Well, I only have one critical number here. It's 5/8. If you change from negative to positive, then it's a relative min. And if you want to imagine this, you can kind of see that we're going down here, and then plus we're going up. So yes, this is a minimum point. So therefore, there is a minimum, a relative minimum at x is equal to 5/8. Cool. Isn't that neat? So it's really just an extension of yesterday's lesson. If you have the sign diagram, you can then figure out what's happening at these critical points. Let's move on to a more difficult example. Okay, our second example. Given the function y is equal to blah, 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 calculate the critical points and determine if they are local maxima or local minima. So there we go, local, remember that's another way of saying relative max or relative min. So we're just going to underline those words just to remember that they're the same thing. Okay, so to do this, I need my critical points. To find my critical points, I need to find the derivative. Now I'm going to write this out as dy dx. Remember, that's another way of writing the derivative, especially when it's y like this. There's a few different notations for the derivative. Okay, so now I'm going to bring down the exponent. So I get 12 x3, what's this, minus 48, 16 times 3, x squared, plus 48x. And the derivative of negative 9 is 0. Okay, now to find the critical points, we set dy dx equal to 0. So I end up with, technically I should be looking for where dy dx does not exist, but again, I know it's not really going to happen for this question because it's a polynomial. So I get 0 is equal to 12x cubed minus 48x squared plus 48x. Then I'm going to factor out what's common here. Well, there's a 12 is common to both of these, and x is common to both of these. So I end up with x squared minus 4x plus 4. And if I factor that, I end up with 0 is equal to 12x, x minus 2, and x minus 2 again. So x minus 2 squared. What makes this true then? Well, this is true if x is equal to 2, but it's also true if x is equal to 0. That's what that first factor means there, right? This whole idea is that any one of these factors, if they are 0, will make this 0. So if x is 0, that makes the whole thing 0. If x minus 2 is 0, in other words, if x is equal to 2, then this factor will be 0. Okay, so now I have my critical points. What do I have to do again? Oh yes, I need a sign diagram. So I'm going to get my ruler, which I seem to have misplaced. Oh no, I found it. Don't worry. And I'm going to draw a sign diagram up here. This is the sign of f prime at x. And what are my points? 0 and 2. So I have 0 and 2. Remember, I'm making a number line for the sign of f prime at x, and these are the x values. So now I need to figure out what's happening at each of these intervals. Again, the easiest way to do this is to draw that table that we did yesterday. We could have done the table in the last example, but it was such an easy example we didn't need to. But for this, it's a good idea to kind of keep track of what we're doing. So I'm going to draw a table with 3 intervals. So 1, 2, 3, and then I probably need one more line here. Okay, so I have an interval x is less than 0. I have an interval x is between 0 and 2. I have an interval x is greater than 2. Then I have all of the factors. Remember, on the left side of my table, I have to put all of the factors. So I factored it here. So I had a 12, an x, and an x minus 2 all squared. Now is the fun part. I get to choose numbers and fill in the signs and then calculate the result. Well, x is less than 0. Let's choose a number, -1. Well, 12 is going to be positive. In fact, 12 is always going to be positive. Okay, if I take -1, this becomes negative. If I take -1, this becomes -3 squared becomes positive. In fact, because this is squared, it always is positive. So then I need to do this one here, choose a number between 0 and 2. I would choose the number 1, put that in here, it's positive. Greater than 2, also positive. My table is quickly finished. Now to calculate the sign of all of these, when I multiply them together, it's easiest just to count the number of negatives. If you have an odd number of negatives, like here, the answer is negative. If you have an even number of negatives, in this case 0 negatives, then it's positive. So I have my sign then, which I now have figured out, is negative plus plus. Okay, now let's see if we can figure out. Remember what the question was. Calculate the critical points and determine if they are local maximum or local minimum. Well, I have, okay, so here, if you want to imagine the function, the derivative is telling me that the function is going down and then it's going up, right? Negative, positive. So therefore, I know there is a local minimum at x is equal to 0. Now what about at x equals 2? Well, I'm going from positive, positive. So because there's no change in sign, there is no local max or min here, so that's it. There's only the one local minimum in this function. Okay. Let's move on to rational functions. Actually, before we get to our final example, let's just talk a little bit more about this. And we need to be really clear and make sure we understand, just like before. Just because the derivative is 0, just because there's a critical point, doesn't mean that there's a max or min, guaranteed. It only is a maximum or min if it goes from plus to minus or minus to plus. Similarly, the points where the derivative does not exist usually correspond to something odd about the function. They correspond to an asymptote or some other feature. We have to be careful because some cases where the derivative doesn't exist doesn't necessarily mean that there's a max or min there. It could be something else. So one example of what you could see is you could have an asymptote there. So you could have some sort of rational function. So this goes like this, and this goes like this. You guys remember a function like that? And in this case, this is C here. So I would say that f prime at C does not exist. So in this case, even though this is a critical number, doesn't matter. There can't be a max or min here because there is no function here. There is no place that could be a max or min. So this is a case where you have an asymptote at that critical number. So there's no max or min. An example of this would be, for example, would be y is equal to 1 over x. There's no max or min on that function. There's an asymptote at the critical value. Another situation you could have would be this neat shape, which is called a cusp. So this is my critical point there, or my critical number. In this case, I have a function that's decreasing. In this case, I have a function that's increasing. So you might be inclined to believe that, oh dear, yeah, you might be inclined to believe that this would be a negative, a minimum. But it's actually not. This is the, at this point, at this cusp point, the derivative does not exist. Now, this is not really in the IB course. Actually, it's not in the IB course. I can be sure of that. I just wanted to show you that, like, kind of one of these points. There are certain shapes, and this cusp shape is one where there is no derivative at this point. So there's no derivative here. But we do go from, so we have, yeah, derivative does not exist, which is a weird thing we don't cover in this course. But we go from decreasing to increasing. So actually, sorry, there is a local min here. Think of this as a piecewise function. So it's similar issue to a piecewise function. Ooh, if I could learn to spell. In this case, the relative max or min exists. Again, this is not really covered in IB. An example, though, if you must know, an example of a function with a cusp would be y is equal to x to the 2/3. So even though there is a point where there's no derivative, there's still decrease, increase, so the max min exists. This one's cool because actually here it's decreasing and here it's decreasing, so that's why it doesn't pass it doesn't change signs. Okay, final one. Again, this is not really in this course, but just to show you so you have complete notes and complete idea of how this course works. You have a vertical tangent. So you have a point here, that's my critical number, where the derivative does not exist. Because the horizontal, for a split second, the tangent line would be vertical, which is impossible. You have on to the left a region of increasing. You have on the right a region of decreasing. So because there's no sign change, you have no max or min. If you must know, an example of this would be y is equal to x to the 3rd. Okay. I just want to put those up there. I try to have complete notes for you. But let me get a different colored pen and just certify that this is not in IB. This is just so that when you get to this in university and you're like, what is a cusp? At least I can say I told you on section 8.2 or whatever this is. So this is not in IB. It's not in IB SL. It's in the HL course, but we're not covering that. So do not study that. Okay, with that in mind, let's go to our final example. Given the function f of x equals x squared minus 4 over x squared minus 1, calculate the relative extrema. Now remember, relative, local, that means kind of the peaks and valleys we're looking for. Extrema means max or min point. And this is a rational function. So we know there are some x values for which this function doesn't exist and the derivative doesn't exist. So let's take a look at this. If I want to find the max min points, I have to follow the strategy I used before. I need to know the derivative. So let me write the derivative over here. Now, unfortunately, this is a function over a function, so I'm going to have to use the quotient rule. So the derivative of the first thing is 2x times the bottom thing, x squared minus 1, minus the top thing, which is x squared minus 4, times the derivative of the bottom thing, which is 2x, all over the denominator squared. Now let me clean this up a little bit. Remember, the goal is to get it so that it's a bunch of factors. So let me expand the 2x. So I get 2x cubed minus 2x minus 2x cubed. Then we get minus 8x minus minus, so plus 8x over x squared minus 1 to the power of 2. Okay, and now I end up with 2x minus 2x, so I end up with, was it 6x over x squared minus 1 all squared. Okay, so that's a pretty good factored version of my derivative. Now, to find the max-min points, or the extrema, I need the critical numbers first. So for critical numbers, there are two situations where this arises. The one we've seen so far is to set the denominator equal to 0. So I have 0 is equal to 6x over x squared minus 1 all squared. I cross multiply, so I get 0 is equal to 6x, so I get x is equal to 0. Now the other one, you can't forget the other one, is to set the denominator equal to 0. So I have this denominator, x squared minus 1 all squared is equal to 0. I'm going to take the square root of both sides. Then I'm going to bring the 1 over to the other side. Then I have to take the square root of both sides. So I end up with x is equal to plus or minus 1. Hopefully you remember how to do that. The square root of 1 is plus 1 or minus 1. So now I have actually 3 critical numbers. My next step though, it's not enough to just know my critical numbers. I have to check the sign diagram, and remember I have to see a change in sign. Those are the 2 necessary conditions. So I'm going to draw the sign diagram that I'm trying to fill out. So here's the number line. Remember what I'm writing here is the sign of the derivative. And then I'm going to put on all these points. So I have negative 1, 0, and 1. They're all critical points, but they're not necessarily a max or min. Now I need to draw my table to help me calculate the signs in each of these sections. So there's 1, 2, 3, 4 intervals plus the first column. Let's try to fit all this in. So I have first column, I have interval 1, 2, 3, 4. And then down here I have my result. Okay, so I have an interval where it says x is less than negative 1. I have an interval where x is between negative 1 and 0. I have an interval where x is between 0 and 1. And I have an interval where x is greater than 1. And my factors are 6. I mean, I can do 6x even. Watch how this would work. And then I have x squared minus 1 all squared. So in this case, I didn't separate the 6. I kept it with the x. But you'll see it's the same strategy. So here we go. Let's take a very negative number, negative 2. This becomes negative. I put the negative 2 in here. I get negative 2 squared, which is positive, and then minus 1 is positive, but no matter what, I'm always squaring my answer. So actually this will be positive this time, but it'll be positive every time. And this, if I gotta choose a number between negative 1 and 0, so say negative 0.5, this will be negative. If I choose a positive, this will be positive, this will be positive. Then I have odd number of negative signs, so this is negative, this is negative, this is positive, this is positive. So I can fill in my sign diagram, negative, negative, positive, positive, like that. Great. Okay, so what does this mean? Well, remember, for something to be a max or min, or a local max or min, or a relative max or min, it has to be a critical number, and it has to change sign. So there's no sign change here, there's no sign change here. Here we're going down, it's a decreasing function, and then an increasing function. So it has to be a local or relative minimum. Therefore, there is a local, sorry, we call it relative min at x equals 0. Now, you may be thinking, well, no, you may be wondering, how is the rest of this chapter going to go? Well, I can give you a little preview here. We know there's a relative minimum at x equals 0. We don't know where that the actual point is on this function. So I'm just going to do a little aside here, but to know the coordinates of the relative min, we sub x equals 0 into the original function f at x. So I can just do that quickly here. F at 0 is going to be 0 squared minus 4 over 0 squared minus 1. So that gives me negative 4 over negative 1, which is just 4. Therefore, 0, 4 is a relative min. So that's something that we're going to be doing later. So we've got to actually calculate the y value. And again, like, not to really spoil where we're going with this, but like, if you're wondering what this function looks like, so we know that there's a minimum at 0, 4. So somewhere, if you want to say somewhere here. So we know it goes up on this side and this side. So you're wondering, well, what's happening at -1 and 1? Well, this is a decreasing function in both cases, and we know that those are both going to be asymptotes. We'll find out. We'll talk about this more later. But if I put in a -1 or a 1 here, this function will not exist. So there's actually an asymptote at -1, an asymptote at -2, and what we find is that this function goes up like that, and then it's some sort of function like this. Just so you get an idea. So it's decreasing, then there's a spot where it's neither increasing nor decreasing, then the function's decreasing again, then the function reaches a minimum, then it's increasing, then there's a space where it's not increasing or decreasing, and then it's increasing again. So that's a little preview to the types of crazy functions you're going to be able to draw by the end of this chapter. And so your homework for tonight is page 234, number 1 to 8. Good luck with that, and we'll see you next time.